So welcome everybody on YouTube. I'm sitting here teaching abstract algebra class, and one of my students asked a really good question. I haven't even defined groups yet, but we like to, get some intuition going before we get into the technical details. And the question was, I showed how the rotational symmetries of the square and the plane, there were 4 rotational symmetries in this of the square and the plane. And then I also talked about this group that had 4 elements, 0, 1, 2, and 3. And when I could add them and get an element back by looking at its remainder mod 4. And the question was, were those 2 groups the same because they both had 4 elements? And the answer is no. And let me show you 2 groups that both have 4 elements that have a very, very different structure. Okay. And however, maybe I'll start with these 2 groups of 4 elements that have the same structure. All right. So let's start with rotations of the square. The elements of this group are rotating by 0 degrees. Okay, and let me save myself some time. Okay, or you could rotate by 90 degrees. All right, so 90 degrees is like that. Or you could rotate by 180 degrees. All right, so that would be this rotation. And finally, you could rotate by 270 degrees. All right, so 270 degrees would be like that. All right, so what I've done is I have 4 elements in this group, rotate by 0, 90, 180, or 270. I've taken those 4 elements and I've drawn them down here as well vertically. And now what this table contains for me is this square is the symmetry that I get by first doing this operation and then this operation. So rotating by 180 degrees is what I get if I first rotate by 90 degrees and then by 90 degrees again. Do you see that? Let's verify another entry. Let's verify this entry. So 0 degrees is what I get if I first rotate by 180 degrees and then rotate by 180 degrees again. And then let's do this. 90 degrees, that is what I get if I first rotate by 270 and then by 180. Let me check. Yep, I indeed got this rotation just by 90 degrees. Okay, this is called a multiplication table. It tells you how to take 2 group elements, one on for the column, one for the row, and it shows you how to take 2 of them and multiply them to get this one. All right, so I also had this other group that cryptically I called Z mod 4Z, but its elements were 0 and 1 and 2 and 3. And when you add them just like normal, but you take the remainder after dividing by 4. So what is 1 plus 1? It's 2. And what is 2 plus 1? It's 3. And what is 3 plus 2? Well, it's 5. And then you take the remainder modulo, remainder after dividing by 4, and you get 1. So visually, do you see this diagonal structure, right? That diagonal structure is the same in both of these groups. And that's not the rigorous definition of what it means for these groups to be the same, but for all practical purposes, That's why we call these groups the same. That's why they're isomorphic. Okay. I'm going a little bit longer than I want to, but let me tell you that there's one other group of size 4. Okay. And this is called the Klein 4 group. One way you can write its elements are as ordered pairs. So 0, 0, 1, 0. Let me use colors. All right. So 0, 0 is one element. Um, 1, 0 is another element. And then another element is 0, 1. And then our final element is 1, 0. Or sorry, 1, 1. All right. So I haven't told you how to add 2 elements of this group. So how in the world do I add, for example, 1, 0 with 0, 1? Okay. What you do is you add component-wise. So I add the first components, I add 1 and 0, and I get 1. And then I add the second components, I add 0 and 1, and I get 1. See that? So that's why 1, 0 plus 0, 1 is 1, 1. Now this addition in each component is sort of modulo 2. You always take the remainder mod 2. So that's why, for example, 1, 1 plus 1, 0 is 0, 1, because when I add the first components, I add 1 plus 1, which is 2, and then its remainder when I divide by 2 is 0. And then when I take the second components, 1 and 0, and add them, I just get 1. All right, so that was a little fast, and no worries if you didn't fully catch that group. But the point is that it has a different structure. We no longer have these diagonal bands, right? Instead, we would have what I would call this checkerboard structure, right? Here's this checkerboard. Do you see that? And so there's no way to sort of rename the elements to turn this checkerboard structure of the Klein 4 group into this banded structure of Z mod 4Z. All right. Any public questions? Thanks so much.